So welcome to this Genie webinar. My name is Ben Newton. I am a graduate student at the University of North Carolina at Chapel Hill, and this is actually going to be the last of the webinars that I will be hosting. I successfully defended my dissertation a few weeks ago and am on my way out. So, but we anticipate that somebody else will be hosting the webinars and we will start them up again in the fall. It is my pleasure at this time to introduce to you our presenter for today's webinar. He has received a PhD from Princeton University and then worked at Microsoft on the Windows Azure team. And there he led the engineering and research for the architecture, the management of the data center networks there, and he is now the director of system architecture at Barefoot Networks and is working actively on the P4 language consortium. And it's my pleasure to introduce to you Chang Kim, and we'll turn the time over to him for his presentation.
Thank you, Ben, for the introduction. Hi, everyone. I'm Chang Kim, and Ben, should I just share my screen and then start presentation? Okay.
That's great. Yeah, please.
Okay. So happy to present these slides and then introduce this technology and very interesting trend to this Genie community. So this is all about programming the network data plane. You probably have heard about programming the network control plane because that has been one of the main themes in the networking industry and research community for quite a while. And it has been known as SDN approach. But now this is going one step further, and then we're trying to make every aspect of networking programmable. And then the last bastion host, in my opinion, was the data plane. It remained as a black box resisting to the trend toward programmability. Now it's opening up, and today's talk is all about that and what it means for us, especially to Genie community like you. Okay. So as Ben mentioned, I work for Barefoot Networks, but I also spend a lot of time to contribute our ideas and technologies to this P4 language consortium. So today I'm wearing more like a language consortium presenters or representatives hat here. So let's start with status quo. Suppose you want to build a networking system today, and by the way, this is high-speed networking system. The first thing you need to do is actually understanding or figuring out what kind of underlying ASICs or packet processing engines you're going to use in the data plane. And then somehow you have to roughly figure out how this ASIC works. And then you write your own, networking control plane applications such as routing protocols. And then you ship this system, and in the field at runtime, the control plane applications use the runtime API and the driver to communicate with the data plane. And then the system starts to work. So this process has actually quite a few problems. First, this communication, right? The guy who writes the control plane applications need to know about the way data plane works. This communication is done in human language, which is quite ambitious, it's ambiguous. And it doesn't matter even if these two groups are actually working in the same company, even in the same large company, they still communicate in English. So that's a problem. The second, more important problem is that this underlying data plane technology is basically fixed. Once the ASIC is delivered and designed, you can't change it. So this introduces a lot of problems, especially very long and unpredictable lead time for new features and ambiguity that is just inevitable with human language-based communication is, very easy to introduce the bugs. Now, let's think about the other way here. So we're all researchers or grad students, and we all have lots of beautiful ideas that we wanted to test and then eventually put into production. But there's extremely limited way of making that possible today. And that's mainly because there's no DIY model here. You always have to work with vendors at individual feature level, at your protocol level. And we all know that it's really, really painful to run that consensus protocol through which you can affect the vendors, because you have to either build both technical consensus as well as economical consensus to incentivize the vendors who will be willing to deliver these features for you. But even if you succeeded at that, you have to wait 3 years, 4 years. That's very long and unpredictable. And to use those features, even after waiting 3 years, you have to usually buy new boxes, new hardware. You can't just upgrade your software and then start to enjoy that feature. But oftentimes, the most painful part is this last part. After having waited 3, 4 years, you got these new features with new boxes, and then you realize that, oh, there is important but subtle difference between what I have asked for and what they have actually delivered. So your 3 years, 4 years were not that useful at that point in time. So, and obviously, if you had programmability in the data plane or everywhere in the networking system, you could have solved this problem much more easily on your own. And then there are such solutions available, right? Of course, you can use CPUs. If your target performance goal is low enough, a few tens of gigabps, you can write your own program, build your own networking system. Very easy. If your goal is slightly higher, you could use FPGAs or NPUs, but still at the range of hundreds of gigabps. But one of the very important and exciting trend that is going on right now in the industry is this thing called protocol independent switch architecture, which we call this PISA architecture. And then essentially this allows full programmability in the data plane, and these chips actually work at multiple terabps today, and then soon maybe some tens of terabps. So the initial architecture of this kind of system was proposed, actually discussed in a few recent papers, including the RMT one published at CCOM 2013. But essentially these machines are high-speed packet processing machines with fully programmable parser and generic match action logic. So in a sense, this is a very different machine architecture than general purpose CPUs or NPUs. And more importantly, this architecture actually proves that the high performance and the programmability can be achieved without any penalty inside chip size or cost or power consumption. And therefore, programmability is not something that it's not a scapegoat of performance, high performance anymore. And the instances of this architecture, let's call it PISA products, are available now. And Barefoot is actually delivering one of those solutions. But the other companies have built an early version of similar architecture. So for example, Cavium has their own programmable networking chips running at 3.2 terabps. And then Intel has also delivered what, if I may call, proto-PISA architecture solutions. Their Flex Switch does something similar. So we're now observing that this kind of PISA architecture is actually, the chips that realize PISA architecture is actually up on the horizon, available right now in the market. And then I predict that this kind of silicon will dominate the networking market in the near future. So today's talk is about understanding what kind of machine this is, how we can use this, and then why this is useful. Okay. So just to recap, why is high speed and yet fully programmable networking is a big deal? This is why. So this is the how switching chips have grown in terms of its throughput over last maybe 10 or 15, 20 years. And the y-axis is a log scale. So switching speed today is about 6.4 terabps. And if you plot the CPU speed, there has always been a gap, almost an order of magnitude gap between the switching chip throughput and the CPU throughput. And today, that is actually almost like 80x, closer to now 2 orders of magnitude difference. So what this means is that as CPU gets faster, the networking chip has to be even faster, and therefore the devices that will interconnect a large number of CPU cores will still have to always be built in this ASIC format. And therefore, adding programmability in that model is such a big deal, and that's going to be very useful to many people, not just researchers, but just real engineers as well. At the same time, this is sort of kind of a trend that is happening in the computing industry over many decades. So I just wanted to emphasize the inevitability of this trend. I mean, explaining why this is possible right now takes probably another 5-minute, 10-minute discussion. But assuming that it is possible right now, this slide just shows you that why that trend is inevitable. So we know that, CPUs, nobody builds specific application functionality in the CPU itself. CPU is just a programmable target, and then application engineers write their programs using high-level language. This happened in the GPU industry as well. The top-performing GPUs today are all programmable GPUs, and then people program that using domain-specific language, OpenCL. DSP went through the same thing. Initially, DSPs implemented fixed function, Fourier transform logic, and a lot of those things in hardware. Now, nobody builds DSPs. Nobody uses DSP that way. The high-performance DSPs are all programmable. People use something like MATLAB to design their own signal processing logic. The same is just happening in the machine learning domain. There is a domain-specific processor called TPU, for example, and then people use other high-level languages to program that machine. Now, the question is, what about networking? Why isn't this happening in networking? And then what we're telling is that this is just about to happen right now. And then Barefoot delivered one such instance, PISA instance chip. And the language that this networking community is proposing and working together right now for this purpose is P4. Another thing that I wanted to emphasize is that once this transition from the fixed function hardware to programmable hardware happens in each particular domain, that transformation is irreversible, meaning that the industry completely changes and they never go back to the fixed function model. The reason is because once programmability is out there, application developers just cannot even imagine a word without programmability. Think about the mobile phone industries today. Can you even think of using feature phones or writing applications for feature phones? It's completely gone. Nobody will go back to feature phone era. Right now, everything is smartphones. Okay, so now these programmable high-speed networking chips are available. PISA is available, and therefore people wanted to come up with a nice domain-specific language that is really friendly and that is easy to consume from the network engineer's point of view. And that's one such attempt was actually P4. And this paper was actually published almost about 3 years ago at CCR. And a lot of researchers and then industry leaders got together and then proposed the initial idea. And this was a short paper, and then we actually decided to build a language consortium to nurture this effort. And so this language is not just a thought experiment or short paper, it's actually an industry-wide sort of open source specification at this point. So if you have this kind of technologies, and obviously this turns the entire picture upside down. So if you want to build your own switching system, you will first dictate using a precise language, machine language P4, that, hey, this data plane should work exactly this way. It should process packets precisely this way. And then in the field at runtime, your existing applications will still communicate with the chips through the runtime API and driver. That path does not change. So P4 is used for this specification. And what does this mean then? So to network device vendors, to the people who need to build and design a networking system, this means a lot of good stories. First, they can now use software programming practices and tools using almost in every phase of their development and testing phases. And that allows them to move very fast and then release lots of new features very easily. Moreover, even if they use the same kind of chips, they can differentiate themselves very easily because it's a matter of writing different people programs to be able to sort of make their systems more attractive. Also, a lot of bugs that are in the people programs can actually be fixed in the field. So, so in my opinion, no software is perfect in the first time, but how robust will the system will eventually be? It all depends on how quickly you can revise the software. And then P4 ecosystem allows the system vendors to revisit their issues very quickly. So very quickly, the systems that will be built using P4 will show much better performance and robustness. At the same time, this is the viewpoint from the P4 switching system consumers side. So if you're building your own network, either as a large online service providers or carriers, this means that there is no more black box in your white box switches. Your white box was sort of really a little gray because control plane was entirely owned by you, but data plane still had one big black box, which is the chip itself. Now, even that chip is becoming transparent, so it becomes a truly white box. Your developers can now program, test, and debug your network devices all the way down because there is nothing that prevents your developers to understand the behavior of your networking system, either in the data plane or control plane. And finally, and more importantly, if you wanted to introduce your own exciting new ideas, new congestion control protocols, new data plane protocols, new encapsulation formats, new monitoring capabilities, whatever, you keep your ideas on your own because the program that you have written is yours. You don't even need to share that with other vendors. Okay? And why do this matter to the Genie community, in my opinion, or the research community? Because researchers always wear both hats. So all these are, in my opinion, very good news to the researchers. So the rest of the talk, I'm going to talk about how this PISA architecture actually works. And then I'll explain why we call it protocol independent forwarding. And then I'll also give a quick example of cool applications that you can actually realize using PISA and P4. And then finally, I'm going to give a quick demo here. Okay. So what is PISA? It's essentially an architecture, a new machine architecture for high-speed programmable packet processing. And so PISA stands for Protocol Independent Switch Architecture. So this is a really high-level diagram explaining the way PISA works. So on the left-hand side, the wires arrive, and then the input packet, the serialized input packet arrives, and then the first thing this machine does is parsing. So you have fully programmable packet parser, and then you can see that there is a multiple stages of match action pipeline here. So in each stage, you have multiple match action units. And therefore, the things that can be parallelized can be scheduled together, but the things that cannot be parallelized because they have data dependencies, read-write dependencies, write-write dependencies, and so on, those things are going to be scheduled in sequence because we have multiple stages. Okay. So when a packet arrives, what the packet parser does is essentially extracting the header fields and headers into some containers, which we call packet header vectors. And then these packet header vectors are used as the containers that contain the match keys. So you look up the table using the match keys, And then based on the match entries, you perform some actions, packet modification actions, other state modification actions, and so on. And then these, as a result, it'll generate a new values in the containers, or maybe an addition or deletion of the existing containers if you want to say add or delete packet headers. This new set of containers with new values will go to the next stage, do the same thing, or maybe different thing depending on how you have written your program. And then this similar process just continues. And then finally, these packet headers are reassembled so that the packet in a serialized format can leave the system. Okay. So this is really a high-level picture of PISA. And of course, to make the system useful, you have to have ingress and egress. So you will have the same copy again on the egress side. So the ingress essentially is just pre-switching packet processing, and the egress is post-switching packet processing. And then the switching is done by the buffer or traffic manager connecting between the ingress and egress ports. Okay. So let's take a little deeper look here. To make this system useful, of course, we need interconnection with the CPU or the switch control plane. So there will be a path connecting the control plane to this data plane chip. At the same time, we can introduce a programmable, fully programmable packet generator so that you can actually generate a lot of interesting events even without relying on the slow CPU control plane. To make these things even more exciting, we can introduce a few recirculation paths, because some packets may actually need a lot of complicated processing match action stages. In that case, one stage or one pass may not be enough. So if you want to do multiple passes, this recirculation will be quite useful. Now, let's look at the match logic here. So essentially, match logic is just a mix of SRAM and TCAM that can store the table entries, and then you can perform associative lookups against these table entries, either exact matching or ternary matching. It also has some other types of stateful memory that are useful for counting and metering, or some generic hashing, essentially an array of stateful registers. So these are used as sort of lookup processing. And then once you look up the table, you have a match, and then that match, each match can dictate a particular action for that match entry. And so action logic is essentially a very simple ALU that does standard Boolean arithmetic operations, header modification operations, or some hashing operations. So now, why do we call this protocol-independent packet processing? And the answer is simple. The reason is because this device does nothing until it actually gets programmed. So this lower level, this lower half of this diagram shows just the PISA pipeline in a simplified format. And then packets keep coming in a pipeline fashion. Of course, to make this useful, you have to define your own logical data plane logic. And that's exactly what your P4 program does. So essentially, this upper half of this diagram is a visual representation of a P4 program. And suppose you have this simple P program that does L2 lookup first, followed by either IPv4, v6 lookup, and then followed by echo. Okay. You write this P4 program, and then you compile it, and what the compiler does is this resource mapping. It figures out that, oh, L2 has to be done first because based on the dependency analysis, it comes first. And you also define the size of this L2 table. So taking into account that information, the compiler will figure out the right amount of physical resources, SRAM or TCAM, match action, MAU counts, counters and meters and so on. And then that resource mapping is actually done by the compiler. Okay. So what if you decide to change your P4 program either in the field or during your development process? For example, you decide to introduce a new encapsulation header and new table for that, say my encap table. And it's a layer 2.5 encapsulation protocol, so it comes between L2 and L3. Now you have changed your P4 program. you recompile it, and then the compiler will find out the best resource mapping, again, taking into account this new dependency chain and then resource demand. Okay. So now, then the obvious question is, what exactly does the compiler do? I mean, explaining this in a full picture will take probably another white paper, but I just wanted to give the high-level sense in this particular slide. So let's look at one particular match action unit instance. Essentially, it looks like this. So this PHBs, the packet header containers that I mentioned, is accessible by all the MAUs in that stage. But this particular MAU instance can access any PHB values because we have highly programmable crossbar here. And then that crossbar can generate the keys for the lookup, and then the keys can be used as it is, or the keys can also be hashed and then used as a lookup key. So there is that hash generation and then multiplexer, and then the key is now used as actually fed into the match table to do associative lookup. And then as a result of that lookup, you have the associated action and instruction, pointing out what you want to do for that particular match entry. And then the result is fed into the ALUs as the parameters along with the instruction itself. And then of course, some of the original packet header vectors are also another, or some other types of ALU operands. And then once you execute this instruction, you get new contents of the packet header vectors or the containers. So that's the output of this stage. So what the compiler does is essentially configuring the way these individual modules actually work, taking into account the P4 program descriptions. So it actually allocates these containers to the particular header fields and headers. It configures the way crossbar should work for this particular stage, how hash generators should work, how this multiplexer should work. It also partitioned the generic SRM TCAM memory into tables and so on. So that's what exactly the compiler does at the compile time. Okay. So now let's look at a sample P4 program here. So it's pretty intuitive. So you defined your own headers, or maybe existing headers such as Ethernet, IPv4, V6, and so on. And header definition is really straightforward. As you can see, this is the header definition of an Ethernet frame. So you have destination addresses, source addresses, either type, and then you can introduce, for example, your own encapsulation header format. Once you define headers, you need to define the parsing logic, and then parser is essentially an instance of stateful, just state machine, finite state machine. So finite state machine can be easily modeled as a transition model. So in this case, it shows the Ethernet stage here. So the first thing that you do is you extract the Ethernet header, and then based on the extracted Ethernet header, you look at the ether type, and then depending on the values of that ether type, you basically can dictate the next state of this finite state machine. Okay, so pretty straightforward here. Once you define your own headers and parsing logic, the next thing you need to do is defining your own tables. So let's look at IPv4 table as an example. It's a really simplified example that is supposed to fit in this simple diagram, but even the real, P4 program doesn't look that different from this sample. So reads specify the set of keys that you have to use to look up these tables. In this case, you have only one key, which is the destination address of the IPv4 header, but you can have VRFs or other keys as a concatenated key. And then the actions clause defines the specific actions that can actually be executed whenever you have a matching against this table. So, and of course, each of these actions is composable, meaning that it's a user-driven. So set next up, for example, is what you can write on your own. And then the body of this action, set next up, is actually comprised of multiple primitive actions, such as modify field, add to field. And these primitive actions are essentially something similar to instruction set. So modify field, add to field, as the name indicates, something that modifies the field values in a header, and add to field adds something to the existing field. You can introduce your own headers, and you can delete such headers. You can do some basic Boolean arithmetics or other logical operations and so on. So all this basic instruction set is defined as primitive actions in P4 language specification. And you can, using those primitive actions, you can come up with your own custom actions. So once you define your own table and actions associated with the tables, the last thing that you need to do is dictating the order of executing or visiting these tables. So that's what we call control flow. And in this example, you apply the L2 table first, and then my encapsulation table. And then depending on whether you have IPv4 header or v6 header, you apply different LPM tables, and then finally echo table. So again, pretty straightforward. So essentially, this is all. So as you can see, writing P4 program is drastically different from writing C program or writing, Verilog program. It's highly abstracted, and it's declarative, and that's why this is very easy to consume and learn, especially if you're network engineers, not hardware engineers. Okay. So what does a real P4 program look like? So in P4 Language Consortium, we maintain lots of real P4 programs. So this is an excerpt or a quote from that real P4 program. So IPv4 LPM table, obviously this is IPv4 routing table. It uses two fields as a lookup key, ingress metadata.vrf, because we wanted to realize the VRF functionality here. The match semantics associated with the VRF is exact. However, the match semantics that we want to use for the destination address is LPM. And then each match entry that comes out of this table can be associated with one of these actions shown here, either NoOp, L3, L2 switch, and so on. And then you can also specify the size of this table, 64K, for example. So then at the compile time, what it does is that it actually creates this table. The compiler creates this table, but the table is completely empty because that's not the compile time action. But the compiler builds this table, empty table, and then tells it, hey, these are the right lookup keys, and then these are the potential actions for each of the match entries in the table. And then at runtime, later on, your control plane applications will populate or depopulate entries from and to this table. Okay. So now that's almost all about the P4 language, a very quick primer of the language itself. I wanted to talk briefly about this language consortium because this is what we have built to nurture this language building and evolution process. So you can visit p4.org, get a lot of information. Essentially, it maintains the language specification. Right now, we have 3 actively working groups, sort of improving the language specification. Plus, it also they also are trying to define the APIs that are automatically generated as a byproduct of compilation process. So anybody can join this language consortium for free, and then they can chime in. They can join the working group meetings remotely or locally as well. All the key development tools, P4 development tools, are licensed under Apache 2.0, so very permissive. And there are reference P4 programs, compilers, debuggers, other development tools. There's reference P4 software suite, basically sample P4 programs, realizing lots of existing protocols already. And then there's test framework as well. It's open for anybody, and then a lot of individuals, organizations, companies, academic organizations also have joined. 3 key people are sort of guiding this progress of these working groups, and the language consortium. Nick, Jen, and Amin are the current board of directors. And there are many members. This is actually probably about half a year old, so we have many more members. And as you can see, there are a lot of academic and research organizations, solution service providers, target vendors, meaning guys who can actually deliver programmable targets, either NICs, switches, FPGA-based, ASIC-based, software-based, NPU-based, many vendors, you can see them here, system solution providers, and even operators such as Google, Microsoft. So this is a very active community right now. So I think we can skip the first half of this slide, but on the second half, there are several other programmable forwarding targets already available. So as I said, there are P4 programmable hardwares, but also P4 programmable software switching components, such as P4 programmable OVS, P4 programmable eBPF, P4 programmable vector packet processors, or FDIO framework from Cisco. These are all available. And on the hardware side, P4 programmable switches, P4 programmable NICs are all available. So now the last part of this talk is these applications. So why are we doing this? Why are we trying to deliver this fully programmable packet processing data plane? Of course, we wanted to do this because we wanted to do something really cool. Okay. So what kind of cool things are we really talking about? This is almost an unbounded list of things, but I wanted to highlight a few things here. Advanced network monitoring, analysis, and diagnostics. This is getting a lot of attention. Custom traffic monitoring and filtering. And for example, Florida published at NSTI last year. Various mods of congestion control. Of course, you can revisit the explicit congestion control protocols that take advantage of the network level information and knowledge, such as RCP, XCP, TXCP. These things are probably very easily doable if you can modify the data plane yourself. But of course, you can revisit DC, more recent protocols such as DCQCN or Timely, and then try to improve them. Dynamic source routing. You can dictate different paths, not just the shortest path, but you can use utilization aware routing techniques, and then the granularity of that routing can be either packets, flows, or flowlets. A lot of things are possible. Embedding middle box functionalities into the switches, such as doing layer 4 connection load balancing in the switches, some attack prevention or mitigation or detection ideas embedded in the switches. These are all very exciting avenues. Offloading parts of the distributed applications. So up until here, these were mostly L2, L3, L4 networking, but people have started looking into the problems related to, sort of running even part of the applications directly in the network. So some people have actually came up with these switch Paxos or switch KV ideas, essentially using switch as a small but extremely fast key value cache, or running Paxos, part of the Paxos algorithm within the network on the switches directly, so that whenever there is no failure, the switching system, the network itself, works as a consensus provider, and it works really fast at high throughput. Some people even start to talk about jointly optimizing the network and the applications running on the network. For example, mostly ordered multicast, published at NSTI and SOSP a couple of years ago, was a fine example of this joint optimization. But of course, this is, as I said, unbounded list. There are many, many more, and of course, your next CCOM paper ideas, your next NSTI paper ideas, SOSP ideas, OSDI ideas can be actually benefited from data plane programmability and P4. Of course, we can't visit all these things together today, but I just wanted to highlight the first one here, advanced network monitoring, analysis, and diagnostics in particular, because this is getting a lot of limelight these days. And in a sense, you can call this the initial killer application of data plane programmability. So switching the gears slightly, I wanted to point out these fundamental problems that the networking admins always face. So you run your own large network, and the fundamental question is, why can I just instrument every single packet? And then why can I confirm whether that packet was correctly and timely delivered or not? And if not, why not? Okay. And even if yes, how well? Because that establishes your SLA boundary. Unfortunately, no switches and network can today answer these basic questions. And that's very frustrating to me, at least personally. That's why I found these data plane technologies, programmable data plane technologies, very useful and exciting. So I argue that in any network, we need to be able to answer these 4 key questions. So this is a sample network delivering packets from source to destination through a network. Packets are being delivered. The first question that I want to answer is this one. Hey, you packet, how did you come here? Right? Which path did you take to come here? That's the first question. So I wanted to get this kind of answers. I visited this switch at this time and this other switch at other time and so on. Second question, why did you come here? Why did you take that path? So what that means more technically is which match rules, which forwarding rules were applied to this packet to by the switches. Okay. The third question is, how long did it take for you to come here at every single hop? Okay. So I want answers like this. At switch hop 1, I waited 100 nanoseconds, hop 2, 200 nanoseconds, but hop 3, I waited a whopping 19 milliseconds. Okay. And the last question is why? Why did you have to wait that long in that switch? Okay. So that's the fourth question. So I call these 4 questions. In this, for example, the last hop delay happened because I happened to share the same output port with this aggressor flow that sends a huge amount of traffic in a bursty fashion. And therefore, I can tell that, hey, this guy waited a lot, but it was not this guy's problem, it was someone else's problem. Okay. So these 4 key questions, ultimate questions as a network admin, I'm there to say that, hey, with programmable data plane technologies, we can answer these kind of questions without any penalty at all. And why is this possible? Because programmable data planes offer many solutions, but I'm just going to introduce 2 high-level approaches through which we can get answers for all these key questions. The first approach is what we call packet postcards. And let me just quickly explain how it works in this diagram. So on the left-hand side, you see a sender, and then right-hand side, you see a receiver. Packets are sent. This packet, whenever it goes through a switch, the switch extracts some information about the packet, like switch ID, input port ID, egress port ID, switching latency, keeps sending this to this monitor. And then the monitor collects per packet information, per hop information, and then it can essentially replay the entire network history. And then packet sizes, the original packets are not even changing, but you have collected all the information. The downside of this approach is that it can generate lots of extra traffic for monitoring, and therefore you may have to be a little more creative to reduce this volume without losing much information. But it is doable with programmable packet processing technology. The second approach, which is also very promising, is what we call in-band network telemetry. In this model, packets travel, and then switches actually modify the packets to add the metadata information. So in a sense, switches use original data packets as log packets at the same time. So when the switches go through this network, it keeps collecting information. And then at the last hop, the switch or the last hop receiver and those networking stack can collect this information, undo all the changes made to the original packet. And so original packets just go up to the applications or TCP, UDP stack, but you have collected every information you need. So this approach doesn't even need additional packets and also can replay the entire network history. The downside is that packet sizes increase, but a lot of networks, you already use network virtualization, encapsulation, decapsulation frequently. So this oftentimes is not a showstopper at all. So doing something like INT in P4 is very trivial. This is actually a P4 code realizing a particular INT example, collecting switch ID and then queuing latency for every single packet. And then it repurposes TCP options to carry this information. But in P4, you can use many other options. You can introduce your own headers or VXLAN options, Geneva options to be able to collect same kind of information, different fashion. So let me show you a quick demo and then let me get your questions. So actually, to show you a demo, let me show you the demo environment here. So I'm going to build a P4 programmable switching network here. Tofino is our switching chip's name, but it's running at 6.5 terabps. It has 6.2 terabps of background traffic, full line rate, but I reserved 3 ports here to connect this switch to one aggressor sender and one victim sender. And then aggressor sends traffic to aggressor receiver, victim sender sends traffic from its own sender to its own receiver from left to right. So victim will generate a low rate, say about roughly 400 megabps traffic stream, green stream. Occasionally, this aggressor will send very high rate but bursty traffic running at almost about 40 Gbps. And then they happen to share the same output queue on this Tofino switch. And therefore, I wanted to see how this output queue actually works. And then to do that, I actually added this INT P4 program into this Tofino switch. And then this INT program simply collects the queue arrival time and then queue depth that every packet sees. Okay. So that is applied to this output queue and actually every output queue of this switch. And then I run a simple collection analysis and visualization tools at the victim receiver to see what happens at this queue. So what's going to happen is that when there is only this victim flow and INT is enabled, the monitor will quickly realize, oh, the queue is entirely empty. I mean, it's obvious because there is no oversubscription. But when this aggressor flow kicks in, the queue is now oversubscribed, and then the queue buildup will happen, and then the monitor will immediately detect that, oh, the queue is growing and full now. When the aggressor goes away, then the queue will drain quickly, and then the monitor will detect that the queue is empty again. Okay, so this is the demo scenario that I wanted to show. So let me play this video quickly. So I'm just starting that victim flow, only the victim flow here, using this hardware traffic generator attached to this 6.5 terabps P4 programmable switch running INT. So this is the visualization tool. And then this time series shows the real-time queue occupancy. Right now, it appears to be that, but it's actually running, but the queue occupancy is actually 0 because there is only victim flow. I'm just starting the aggressor flow here. Now you can see that occasionally this queue buildup actually happens. And then to understand the details, I actually pause this time series and then click each bar here. And then this bar expands to the real, per packet information chart here, showing how the queue actually grew over time in this short time period in millisecond, sub-millisecond level. More interesting thing here is that now you could actually observe this queue buildup right here. For example, the queue grew this way over a very short time period, almost at a few tens of nanoseconds. And then you can also see that the queue stayed here and then gradually came down. But more interestingly, because I'm collecting, for every single packet, I'm collecting the arrival time at the queue as well as the sojourn time, essentially how long did each packet stay in the queue. With these two information at every packet, I can actually reconstruct the queue composition, meaning that at any given time, I can tell how many bytes from each flow I had in that queue. And that visualization is also possible here. But as you can imagine, the aggressor is much more aggressive than the victim. Therefore, in this case, the vast majority of the queue bytes is actually consumed and occupied by the aggressor. And it's not visible if you use the linear scale on the y-axis. That's why I'm changing the y-axis to log scale. And when you change it to log scale, you can see that, oh yes, indeed, the vast majority of this Q bytes are actually consumed by the aggressor, and then there is a small 1 or 2 packet size or worth of bytes consumed by the victims. So based on this information, you can actually tell that, oh, the victim is suffering, and then the reason why it's suffering is because there is this aggressor flow, and you can identify the 5-tuple of that aggressor flow, try to mitigate that by throttling it or shutting it down or just simply report it. You can do all those kind of things as well. So this showcases the power of great visibility that you can ensure if you own the data plane. And then the sample P4 code that I used is also available on this p4.org webpage. Let me just finally recap the benefits and then conclude the talk and then get your questions. So why is data plane programmability such a big deal? I summarized the key benefits that this programmable forwarding technologies can deliver. First, you can, of course, deliver new features very quickly. You can also reduce your complexity very easily. For example, in data center environment, a lot of people do not use, say, MPLS or IP multicast. So you can get rid of those kind of protocols from the data plane ASIC itself. And that actually increases the amount of memory or other logic that can be repurposed for more valuable things. So that's what I mean by this third point, efficient use of resources. So for example, by getting rid of MPLS functionality and the tables, you can, for example, increase your IPv4 routing table size or echo size. So essentially you can use the hardware resources as flexibly and as efficiently as possible. You can ensure great visibility almost at the packet level, because visibility at the packet level needs modifications in the data plane, because control plane is too slow and data plane is now within the realm of modifiability. Modularity, you can compose your P4, your switch program by basically using someone else's P4 program or P4 libraries. So you can develop your system much more quickly. You can even port, meaning that you write a P4 program once and then use it for different types of programmable devices or future generation of P4 devices. So your design, your networking idea doesn't necessarily need to change only because you change the hardware target. And finally, you can own your own IP. Your P4 program just realizes your ideas. You don't need to share it with your competitors or other people. So in a sense, this is just the first step toward the entire infrastructure programmability. And network is just becoming a programmable platform. And we know that this transformation actually has already happened in computing and storage industries. So really exciting time. And if you want to know more about P4, we're hosting lots of events. So feel free to join the P4 workshop and developer day in mid-May at Stanford. There are also lots of materials and tutorials and demos available on the web. So feel free to dig up and get those information as well. So hope that was useful. And then let me take questions. Ben? Sorry, Ben, I'm not hearing your voice. Oh, actually, sorry, I can't hear you still. Is it my problem or?
It's my problem. Can you hear me?
Okay. Yes.
Sorry. When you add information to the packets,
yeah.
Second monitoring example.
Yeah.
How do you handle? I mean, where do you add that information? Is it a second another header? And if so, how do you handle cases where the packet already has it met its MTU? Do you have to deal with fragmentation? Yeah. So good question. There are actually two questions here. Which fields do you borrow? In P4 world, you don't actually need to borrow things. You can invent new headers. But still, if you want
to borrow the existing ones, you can borrow almost anything. So in that particular demo, I happened to borrow TCP options, but we have implemented other encapsulation formats, for example, VXLAN options. VXLAN is a popular network virtualization encap protocols, and you can actually attach lots of options in a generic fashion. So we have done that. We have also built a Geneva option-based mechanism. Some people have started talking about doing this using custom layer 4.5 encapsulation, meaning that a header that comes even after TCP or UDP header. Some people are doing this using encapsulation that comes between MPLS label and Ethernet frame header, or after MPLS label stack but before IP header. So all these are possible in P4, just different P4 programs. The other question, so what happens when the packet has already reached the MTU maximum? So to prevent that problem, you have to leave enough growth room. So your switch-to-switch link has to take into account this potential growth. So maybe another, say, 64 bytes, 128 bytes. But your traffic sources, for example, NICs or the VM switch or the VNICs, should use an MTU value smaller than that, so that the packets can grow over time within the network. But surprisingly, a lot of enterprises and data centers do not worry about increasing the packets much anymore, because jumbo frame support is already out there, and then people are already doing this network virtualization encapsulation. So what we're proposing using INT is just repeating the same process at every hop, instead of doing it at the first hop and then last hop.
Got it. Thank you.
Sure.
Please, if you have other questions for Cheng, please go ahead. It looks like we just had one that came in the comment in the chat. What happens when requested table size, number of entries, is greater than available space in a PISA target? Does compilation fail, or is there a mechanism to balance available table space?
Yeah, the short answer is that yes, you will get to know about that at the compilation time, because compilation will fail, and good compilers will give you not just the specific error messages saying that, hey, only for this particular table I couldn't fit. But better compilers may even be able to give you other alternatives. Hey, if you reduce these other tables, you may be able to fit this one, and so on. Yeah.
Are there multiple vendors for PISA chips? And if so, how are they spec'd? Is it based on TCAM size, the size of the pipeline? How do you compare these different PISA chips?
Yeah, the main differences will be the amount of physical resources available, as you mentioned. How much raw TCAM does it have? How much raw SRAM does it have? How many stages does it have? And so on.
Okay. And are there multiple vendors out there of PISA chips?
So Barefoot is one of such solution providers, but as I mentioned, Cavium has their all 3.2 terabps programmable ASIC, and Intel actually released FlexSwitch several years ago, which I would say a proto PISA architecture.
Okay.
And yeah, and I know that this is an active research as well as development area. So I predict that sooner we'll probably see a handful number of options very quickly. And on the NIC side, we have even more options already today. So there are NPU-based P4 programmable NICs, as well as FPGA-based P4 programmable NICs. On the software side, yes, VMware and the OVS owner, Bandpath, actually announced officially that he will release P4 programmable OVS software switch Q3 this year. P4 programmable eBPF platform, P4 programmable BPP, vector packet processor, those things are also available.
Thank you.
Yep.
Can I ask a question? Can you hear me?
Sure, yes.
So, I'm a big supporter of Barefoot and P4, and I'll ask the same question I asked before. So P4 is really low-level representation of business logic. So data model in between is pretty much mandatory. I still don't see Yang on GitHub. We discussed it many times, and everybody would benefit from writing really not relatively low level T4 code, but rather high level intent, where T4 code would be the rendering function of the intent data model.
Mm-hmm.
So when do we see Yang models from you?
Are you talking about the high level abstraction than P4?
Yes.
Okay.
P4 is still low level coding. Not very attractive to many networking engineers who don't code.
Yeah. So I see what you mean. So to hardware engineers or to traditional, system developers, P4 is way higher level than, say, physical level SDKs or APIs. But it's still lower level if you, for example, develop routing protocols for, platform or target independent logic, because those protocols, for example, use much more simplified but highly abstracted interfaces. For example, there is SAI from Microsoft or OCP that is higher level than P4 generated API. So that the shim that maps this higher level API to P4 level auto-generated API is an active working thing. And then that's one of the reasons why we created API working group in P4 language consortium. So I believe that language consortium actually announced a roadmap earlier this year saying that this API working group will be the main charter, one of the most active work items. And I think they will announce probably the official kickoff date along with 2 co-chairs of that working group very soon.
Oh, thank you. So perhaps something to look into. And second question, so there's some ongoing work in ITF called in situ ONM, and their name is one of them. So I gave them home in the routing working group, and I would like to see the stuff progressing. It's properly done. There's support from large companies. So when do we see something from Barefoot?
I think we are participating in that activity. I know that one of our engineers are actually working as a co-author of the draft. So yeah, we are actively engaging with the other contributors of that working group, and we're offering feedbacks as sort of ASIC vendor or programmable solution providers working at high performance. Because if you're targeting low performance like 100 Gbps, you can come up with almost any solutions. Because you can realize it using CPU or FPGAs. But we have to meet somewhere in the middle so that the idea in situ AM, in our language, it's in-band network telemetry, can work across a large spectrum of devices. So we're offering a lot of feedback from the hardware point of view.
Great, thank you.
Yep.
Okay, there's several questions that have come into the chat window. Let's cover those and then we can get some more live. So this one's from Varun. What are the ways to simulate P4 without the hardware? Does Docker or a normal VM work?
Yeah, so if you visit p4.org, there is a code page, and then it leads you to the GitHub repository where we keep all these P4 deliverables. So one of the tools that you can use there is what we call behavioral model. It's essentially a P4 programmable software switch that can run in a VM or a container, or it can run through the mininet as well. Yeah. So you can essentially write your own P4 programs, compile it against the behavioral model switch, and then test it today. Can I just take 5 seconds? Somebody is actually asking for this room.
Yeah, no problem, no problem. And while he's taking just a break, I'll just give a little spiel. This is the Genie webinar. We haven't talked much about Genie, but for those who are here and aren't familiar with Genie, Genie is a service that essentially gives you, network testing as a service, network experimentation. And so it's an NSF project that allows you to reserve resources and do all sorts of network experimentation on the Genie resources that are allocated across the United States, and they actually have partnered with other institutions around the world as well. So look into genie.net for more information on Genie. Go ahead, Cheng.
Yes. Okay, so I can take.
Yeah, let's do another one from the chat. This is from Cheng Yu. How could P4 integrated with be integrated with SDN? Let control manage the P4 switch.
Yeah. So good question. So P4 is essentially, in a sense, neutral to SDN or traditional networking because it can cater to the needs of both needs. You can realize actually OpenFlow v1.3 in P4. And in fact, I'm sure that there is a P4 program contributed to P4 Language Consortium realizing a certain version of OpenFlow data plane. So essentially, yes, P4 is a tool that allows you to build a natively designed OpenFlow switch, and you'll be able to run OpenFlow agent on top of such a data plane, and then connect the data plane to the SDN controllers. The benefit of doing that approach is obviously you're now using the whole data plane physical resources to realize OpenFlow data plane. So it's not that you have only a sliver of TCAMs that can be repurposed for OpenFlow, and then the rest is still realizing, the old, L2, L3 legacy routing protocols. Your entire SRAM or TCAM can actually be now used to realize OpenFlow data plane.
Here's another question from Abu Bakar. Is there a controller platform supporting some sort of P4 orchestration? Is there any controller platform supporting some sort of P4 orchestration?
So I'm not sure what the control plane means in this concept. Are we talking about switch local control plane or the remote but logically centralized SDN style controller?
So Abu, if you can give us any more, go ahead and put it in the chat window, or feel free to chime in. Here's one more question from Cheng Yu. What if you want to save packets on switches in network storage like information-centric network, but the chip has limited space? Is it possible to implement such functionality? So how much table memory and how much buffer would P4 programmable target or switch have is target specific constraints. It's like how many, it's almost similar to how much SRAM you have, right? But I would in general say that, hey, because these switches run at multi-tera BPS, they will not have a huge amount of DRAM capacity. It'll be still constrained by the physical reality that is governing the size of SRAM, on-chip SRAM, which will be maybe at most a few tens or hundreds of megabytes for the time being. So I'm not sure whether they will be sufficient for the ICN or content caching like scenarios. If not, maybe one thing they can think of is use this kind of chip for processing, but pair it with DRAM banks or something like that, and then come up with a direct connectivity between the programmable chip and the DRAM banks. So those kind of solutions might be quite interesting. All right, there's a comment from Jeff Tent. ONOS has project to do P4SB, is what he said.
Okay.
A clarification from Abu Bakar. I meant like sending a P4 program from a remote SDN controller to a P4 enabled switch. Is there any effort in the industry towards this? So that's a clarification of his previous question.
Sending a P4 program from a remote SDN controller to a P4, no, there is no industry consensus on that, but it's relatively straightforward thing. I mean, P4 program is something like just a binary. So you just disseminate it through the management channel, and then simply reload the switch with that new binary. That's all.
Great. Another question from Vuren. Is it possible to update the data plane, basically recompile a P4 program without losing any packet and remotely?
That's a great question. So the P4 language specification doesn't dictate the target's behavior. It just says that, hey, all the P4 compliant targets should support in-field runtime reprogramming. The question is, when you do that, how long a disruption would the target actually introduce to the ongoing traffic? So in a sense, this is target-specific constraints. Some targets may be able to introduce zero disruption. Some targets or some compilers may introduce a short disruption, like, I don't know, tens of milliseconds or hundreds of milliseconds. But I would say it's target-specific constraints. Yeah, language allows either way.
And certainly you can do this remotely.
Yeah, triggering this remotely is, yeah.
If I may add to previous question, so the P4 transport should be transaction-based. So there are two suitable protocols, netconf and gRPC. I played with both. gRPC looks just great. It gives you ability to create P4 binding remote and stream it to the device. Works extremely well. There are early prototypes, so I assume we will see P4 bindings on gRPC quite soon in open source.
Yep. Thanks, that's useful. Yep.
Okay, another question from a new person, Ronald Vanderpool. You mentioned the packet generator. Can it also be used for ICMP-like functionality? Can this be described in P4?
Yeah. So that packet generation engine can be quite useful for a lot of things. Yeah, you can handle, for example, ICMP echo request in the data plane directly. You can also do ARP responses and those kind of things. But those things are more traditional networking applications of packet generation engine, but you can be even more creative. Essentially, packet generation engine is an event generator here. So packet doesn't need to be considered just traffic. You can just think of it as an incoming of extremely fine-grained and periodic events. So if you need to do something in your programmable pipeline frequently and periodically, you can use that engine as well.
Great. And I think the last question for now, what about network scheduling? Does P4 support this?
So that's a good question. So right now it doesn't, although it actually is useful for discovering a lot of messages or getting a lot of information from the scheduler or switches or feed something into the switches. So you can affect your scheduling, switching, or queuing behavior significantly using existing P4. For example, in P4 word, RED, random early discard, or something similar to that, any AQM mechanisms are implemented as P4 program running on the egress pipeline based on the queue depth or queuing latency that each packet has observed and then exporting to the egress pipeline. So it's doable, but that doesn't mean that you can change or you can introduce a completely new scheduling algorithm or queuing discipline using P4. P4 is not that kind of language at this point.
Great. What other questions does anybody have?
Hello, can you hear me?
Yes, we can hear you.
Hi, I'm Rodrigo from UFRGS, and I've been using, just started using P4, and I've noticed that sometimes you need extra parsing primitives or even local control logic. And I can easily do that in a software switch like BMV2, but how about switches in general? Do you see if, how do you see that? Do you see a new programmability paradigm for programming switches in actions internally, or do you think that maybe parsing programmability and table programmability is enough?
So I'm not sure if I'm understanding your question correctly. So which specific features are you looking? Which specific features are available in BMV2 software switch but not available on hardware switch?
So like maybe I want a new primitive, not just adding a header, but
are you talking about adding a new primitive action?
Yes, or maybe I want my controller to put a local control logic that doesn't need distributed view of the network, like say L2 learning, which could be implemented directly at the switch.
I see. I see. So that's again target specific things, but at the language level, we allow each target to introduce their own advanced functionalities. That in the language consortium, we call it an exercise to enable the functional heterogeneity. So, for example, some targets, although it may work a little slowly, some people targets may be able to do, say, packet compression or packet encryption. It's unlikely that you can do that at 6.5 terabits or 12.8 terabits, but if you're targeting, say, 400 Gbps, it may be doable. And in that case, the P4 language itself introduced this notion called extern type. So the target provider can actually sort of come up with a simple interface, sort of showing the capability of this encryption capability, model it as an extern type, and then call it it's a target-specific primitive available only on that target. So the P4 programmer can use that extern, instantiate those extern types, and then feed data to encrypt some packets or contents, and then receive encrypted results from the extern instance and so on. So you can model it in the P4 program, but the realization of that extern function is not doable in P4. We assume that it's done either in hardware or some other mechanism.
Thanks. Yeah, thanks.
So there was another chat question.
Yep.
How does P4 handle entry/route updates?
So as I said, P4 at the compile time does not populate the table entries, and table entries are meant to be populated or depopulated or updated by the runtime, by the control applications at the runtime. Okay, but one interesting and important thing here is that when you compile a P4 program, it actually auto-generates the API functions for each table, so that through the APIs, your control applications can actually manipulate the table content. In a sense, you define a new table called table X in your P4 program. When you compile it, the compiler will give you a function, maybe 3 functions: add entry to table X, delete entry from table X, update entry in table X. So that auto-generated API is essentially equivalent to what fixed function ASIC vendors call SDK. Although I really don't think that SDK is the right term. It's more like API. So that runtime table programming API is auto-generated in a P4 world, and your control plane applications just simply consume the auto-generated API to handle your table contents. One really nice consequence of this model is that what that means is that your API is actually an artifact that is derived from your own P4 program. So what that means is that even if you change your targets, different hardware to different generations or across vendors, your API does not change, because when you compile it, you get the same API. As long as you keep using the same P4 program, your API also remains the same, and therefore your control plane can also remain identical.
I think there's a question, follow-up question on that. By runtime API, you actually mean the .h file that is generated by the compiler, right?
Not just the .h file, .c file, the implementation of the API as well.
All right, and there's another question. Do WGs, I assume that's working groups, are they working in new primitives?
We could, if we can discover a really popular and common primitive actions that everybody think that they can implement, we could introduce new primitives. But at this point, we think that the language is quite stable and we have identified most of the primitives we need. There could be some other target-specific primitives. So instead of, in those cases, instead of changing the language core, we decide to sort of support all those various forms of primitive, target-specific primitives using a common mechanism called extern type. So that's, extern type is exactly for that purpose. Can we enable functional heterogeneity of different targets without polluting the language core itself and then generating new languages over time?
What other questions does anybody have?
Okay.
All right.